Quantum physics, also known as quantum mechanics, is a profound branch of science that delves into the behavior of matter and energy at the smallest scales of our universe. It reveals an extraordinary world, challenging the very foundations of classical physics and our understanding of reality. In this 1,000-word exploration, we will journey into the depths of quantum physics, uncovering its principles, enigmatic phenomena, and remarkable technological implications. At its core, quantum physics deals with the fundamental constituents of nature: atoms, molecules, and subatomic particles. In the early 20th century, scientists embarked on a quest to understand the mysteries of the quantum world, and their findings revolutionized science. One of the fundamental principles of quantum physics is wave-particle duality. Unlike classical particles, subatomic entities, such as electrons and photons, exhibit both particle-like and wave-like behaviors. This dual nature bewildered physicists and led to a paradigm shift in our understanding of matter and energy. Another intriguing concept is quantum superposition, which allows particles to exist in multiple states simultaneously. Imagine a coin spinning through the air, showing both heads and tails at the same time. This is the essence of superposition. This idea challenges our classical intuition and opens the door to new possibilities and potential applications. Perhaps the most mysterious and perplexing aspect of quantum physics is entanglement. When particles become entangled, their states become inseparably linked, no matter how far apart they are. This bizarre connection seems to defy the very fabric of reality as we know it, as changes in one entangled particle instantaneously affect its partner. Einstein famously referred to this phenomenon as spooky action at a distance, highlighting the profound implications of entanglement on our understanding of space and time. While the philosophical implications of quantum physics are awe-inspiring, they also have significant practical applications. Quantum mechanics underpins modern technology in various ways. Transistors, the building blocks of all modern electronic devices, operate based on quantum principles. Lasers, essential in countless industries, rely on quantum processes for their functionality. However, the most exciting promise lies in the realm of quantum computing. Traditional computers use bits to process information, represented as zeros and ones. Quantum computers, on the other hand, use quantum bits or qubits, which can exist in multiple states simultaneously, thanks to superposition. This parallelism grants quantum computers unprecedented computational power, enabling them to solve problems that would be practically impossible for classical computers. Fields like cryptography, drug discovery, and optimization are on the cusp of transformation through quantum computing advancements. In the domain of communication, quantum entanglement is reshaping the future of secure networks. The unique properties of entangled particles allow for ultra-secure communication protocols. When a message is transmitted using quantum entanglement, any attempt to intercept or eavesdrop would disturb the entangled state, immediately revealing the breach. This cryptographic technique holds the promise of unbreakable codes, providing unparalleled security for sensitive information exchange. While quantum physics has led to remarkable scientific and technological progress, it also raises profound philosophical questions about the nature of reality and the role of human observation in shaping it. The famous double-slit experiment, in which particles display both wave-like and particle-like behaviors based on whether they are observed or not, challenges our intuitive understanding of causality and the objective nature of the universe. The Copenhagen interpretation, proposed by Niels Bohr and Werner Heisenberg, asserts that the act of observation collapses the quantum state into a definite outcome. In contrast, other interpretations, such as the many worlds hypothesis, suggest that all possible outcomes exist in parallel universes, and the act of observation merely reveals one of these branches. These philosophical questions continue to captivate physicists and philosophers alike, sparking debates and stimulating further research into the foundations of quantum physics. Despite the remarkable progress made in understanding the quantum world, there are still challenges ahead. One of the most significant goals in modern physics is the unification of quantum mechanics with general relativity, Einstein's theory of gravity. The quest for a theory of everything, often referred to as quantum gravity, seeks to reconcile these two pillars of physics and provide a comprehensive framework that encompasses all known physical phenomena. In summary, quantum physics is a mesmerizing journey into the deepest layers of our universe. Its principles defy classical intuition, revealing a world of wave-particle duality, superposition, and entanglement. This enigmatic realm not only challenges our understanding of reality but also holds the potential to revolutionize technology, paving the way for quantum computing and secure communication networks. As we continue our exploration of the quantum world, we are reminded of the words of physicist Richard Feynman. "I think I can safely say that nobody understands quantum mechanics." The quantum realm remains a realm of mystery and wonder, captivating our minds and driving us to push the boundaries of knowledge further. As we unravel the secrets of the quantum universe, we can only imagine the astonishing possibilities that await us in this uncharted territory.